Alright, hello and welcome to what is arithmetic and geometric sequences number 2. We started arithmetic and geometric sequences number 1, where we looked at just arithmetic sequences by themselves. In this lesson, we're going to look at geometric sequences and what they are and what they mean. In terms of the syllabus, this is Unit 1, Topic 5, Subtopic 1 and dot point 1. And we are learning to recognize and use the recursive definition of a geometric sequence. A recursive definition, if you remember from arithmetic sequences, is using the previous term to define the next term in a given sequence. So let's take a look at this. In a geometric sequence or a geometric progression, each term produced is given by multiplying the previous term by a constant value called the common ratio. Some really important vocabulary in here that I want you to know. A geometric sequence, each term is produced by multiplying the previous term by a constant value called the common ratio. Just a quick example for you. I've got the sequence 3, 6, 12, 24, 48, and 96. Now in this sequence, it's a geometric sequence which has a starting value of 3 and a common ratio of 2. Now what we can see is that each term is multiplied by 2. So when I have a look at this, 3 multiplied by 2 is 6, 6 multiplied by 2 is 12, 12 multiplied by 2 is 24, and you can start to see the pattern. Sequence can be written mathematically as 3, or 3 times 2, 3 times 2 times 2, 3 times 2 times 2 times 2, 3 times 2 times 2 times 2 times 2, or another way of writing this is using an index notation. First two terms would be the same, and then I get 3 times 2 squared, 3 times 2 to the power of 3, or 3 times 2 to the power of 4. On this slide, the highlighted sections are the notes that I would like you to take down. Please pause the video if you need to. This is now Unit 1, Topic 5, Subtopic 1, dot point 2, where we're going to actually use the definition for geometric sequence as a mathematical formula. Geometric sequences. Mathematically speaking, the first term of a geometric sequence can be given the name A, and then there's a common ratio that we spoke about on the previous slide, and that's given by R. The first term in any geometric sequence is just A, it's our starting term, and then we multiply each term as we go up by our common ratio. What you'll notice is that we're increasing the power. The nth term of a geometric sequence, with the first term given by A and the common ratio is T subscript n, is equal to AR to the n minus 1. What you should notice with this formula is that the sixth term has a power of 5. That is the sixth term, this is 1, 2, 3, 4, 5. The sixth term has a power of 5, and that's where our n minus 1 comes from. The inductive definition, okay, which it tells us the first term of our sequence, okay. The inductive definition with first term A and common ratio is, well, T1 is equal to A, and then Tn plus 1 is equal to R multiplied by T subscript n. Okay, geometric sequences, and just a quick example for you. Determine the seventh term of a geometric sequence 8, 12, 18, and 27. This is a geometric sequence, and we can immediately see that my first term A is 8, and my common ratio is 1.5. Now, how I found my common ratio there is I did the division or the ratio of consecutive terms. What do I mean by consecutive terms? Consecutive terms are two terms that add one next to one another. So I've got my first term here. My first term is 12, and then the second term is 8. And what you should notice is that the common ratio between any consecutive term, it doesn't matter if you took the 18 and the 12, or if you took the 12 and the 8, the ratio of both of those terms will always be 1.5. And that is the definition of a geometric sequence. Have a look at the nth term. Okay, it would be okay to just multiply up each number by 1.5. For example, to find the next number, you just multiply by 1.5. But we don't want to do that. We want to use the definition. Remember, our formula is Tn is equal to A times R, common ratio, to the power of n minus 7. Well, we're trying to find T7. Keeping in mind our first term is indeed 8, common ratio is 1.5, and our formula requires us to do the power of n take away 1. So 7 take away 1 is 6. Example for us. Example number 2. The third term in a geometric sequence is given by 36, and the sixth term is given by 972. Calculate the first term and the common ratio. I'm not sure if you can see it just now, but we're going to have to do some form of simultaneous equation. The first thing I'm going to do is step out mathematically what information is given in our problem. I've got the third term here, AR squared equals 36. Why have I got AR squared here? Why is it a power of 2? Well, the reason that is because my third term, keep in mind that we subtract 1 from the power, is 36. Having looking at our sixth term here, we will have AR to the 5 equals 972. What I can do is use a process called elimination, or that is solving a simultaneous equation by elimination. And what I can do is find the ratio of those two terms. I can do AR to the power of 5 multiply or divided by AR squared. And if I do that, I will get AR to the power of 5 divided by AR to the power of 2 equals 972 divided by 36. Simplifying this, my A's cancel out with one another, and remembering my inverse laws, R to the power of 5 divided by R squared is just R to the 3. 972 divided by 36 is just 27. To solve this, I need to take the cubed root of both sides, or what I really need to do here is raise both sides to the power of 1/3. Doing this makes the R by itself, and I should get R to equals 3. Perfect. We have successfully solved for our common ratio, and now what we need to do is use one of these formulas up here. We can either use AR squared equals 36, or we can use AR to the power of 5 equals 972 to solve for our A, even though, because we know the R. Let's go ahead and do that. This formula comes from here, and I've just substituted it in my R value. A times 3 squared equals 36. I get there 9A equals 36, and then A equals 4. So what we have here is a sequence, a geometric sequence, with a common ratio of 3 and a starting term of 4. A bit of a tricky example that required us to use a simultaneous equation to solve that one. Okay, this is now Unit 1, Topic 5, Subtopic 1.3, and we're learning the difference between a convergent and a divergent series. Convergent and divergent series. Geometric sequences either converge or diverge. Now let's take a look at what these two mean. Converge means goes to 0. And diverge means goes to infinity. Now, whether a geometric sequence converges or diverges is dependent on our common ratio. For a geometric sequence, if the common ratio is between 0 and 1, the sequence will converge or go to 0. If it's also between 0 and 1 and -1, it will converge to 0. Okay? It doesn't matter if it's a positive or negative number. If it's between 0 and 1, it will always converge or go to 0. I'm going to explain what that means a little bit more, but let's talk about divergent series now. In a divergent series, if the geometric sequence has a common ratio of greater than 1, the sequence will diverge or go to infinity. Now this infinity could be a positive infinity or a negative infinity, and it gets larger and larger without a limit. It means it goes on forever and forever. Let's have a look at a quick example here. The first term of the geometric sequence is 0.2 and the common ratio is -5. The first sequence will look like this. We get 0.2, multiplying that by -5, we get -1. Multiplying by -5 again, we get 5, a positive 5 this time. Multiplying by -5 again, we get -25, then 125, and then -625, so on and so forth. This is an example of a divergent series. If we were to continue this pattern on and on, eventually we would go to infinity. The only geometric sequence that neither converges nor diverges is where the common ratio is actually equal to 1. And in this case here, the starting term would stay the same forever. Just a quick example for you: 4, -4, 4, -4, 4, so on and so forth. Okay, just a quick example involving a convergent series. If the first value of a geometric sequence is 8 and the common ratio is 2 on 8, and that means that we are multiplying each term by the ratio 2 on 8, we get the following sequence. We start with our first sequence, our first term 8, multiplying by 2 on 8 each time. We get 8, 2, a half, 1/8, and then 1 on 32. What you should notice is that if we kept this sequence going for long enough, it will converge to 0. That means that the sequence itself will no longer get bigger. Just a quick example involving convergent series where the common ratio is negative. Now, if the common ratio is negative, you might have noticed this, the signs alternate. So just a quick example for us. The first value of a geometric sequence is 6, and the common ratio is -1/2. What that means is each term gets multiplied by the previous term by a factor of -1/2. And what you should be able to notice is that the first term is positive, the second term is negative, positive, negative, positive, negative. And this is a really important characteristic of geometric sequences where our common ratio is negative, and it stems from the fact that r squared equals a positive number, r cubed equals a negative number, so on and so forth. What I mean by this is if the power is even, we get a positive, and if the power is odd, we get a negative. This is a sequence that converges to 0 because my common ratio is -1/2. It is between 0 and 1. Okay, this is now Unit 1, Topic 5, Subtopic 1, dot point number 4. What we're going to be learning to do is sum the terms or add all of the terms in a geometric sequence. Summing the nth term in a geometric sequence. The sum of all terms in a geometric sequence is called a geometric series. The sum of the first n terms can be given by the following formula. Sn equals all of the terms added together. So the first term plus the second term plus the third term plus the fourth term, so on and so forth till we get to the last term given by a to the r n minus 1. Now, it'd be particularly useful to have a formula for this rather than adding each of the terms individually, and that formula is a, open bracket, r to the n minus 1. Now in this formula, a is my starting value, r is my common ratio, n is my term number, and r is my common ratio again. I'm going to do it the long way for the sake of an example, and then I want you to go ahead and afterwards use the formula that I provided with you to verify and double check my answer. I'm going to do it the long way now. I've got the sum of the first 5 terms of a geometric series with first term 2 and common ratio 3. My first term is 2. I multiply that by 3 to get the second term, multiply that by 3 squared to get the third term, so on and so forth until I get all of my terms, my 5 terms. Using a calculator, 2 times 3 is 6, 2 times 3 squared is 18, 2 times 3 to the 3 is 54, 2 times 3 to the 4 is 162. If you add all of those together, you should get 242. What I would like you to do is pause the video, use this formula where A equals 2, R equals 3, and N equals 5 to verify that the formula works and you get the sum to the first 5 terms equals 242. Okay, this is now Unit 1, Topic 5, Subtopic 1.5, and we're going to be learning to sum to the infinite terms in a sequence. In the previous slide, we summed to the nth term, and that was for divergent sequences. In this case here, we're going to sum to the nth term or to infinity, so infinite terms of a convergent series. The formula is slightly different, however, it uses all of the same principles from the previous example. Okay, the sum to infinity of a geometric series. In the geometric series I've got here, it's a convergent series, which means that the common ratio is between -1 and 1. Now, the sum of the series tends to a particular value as more terms are added, and this is what I'm going to show you. This, in fact, this series here, if we were to add on all of the terms, it tends to 2. If we increase the number of terms to infinity and we were to sum all of these terms, the value we should get is 2. Now what you could do is go ahead and add all these terms up, 1 plus a half plus a quarter plus 1/8 plus a 1/16, and you should get a number closer to 2. And what we'll find is if that we increase the number of terms to infinity, we should get exactly 2. Let me show you in a diagram. Suppose we have a square and it has an area of 1 and it's 1 unit by 1 unit long, and then we add a rectangle that is 2 units long, and then we keep adding, and I hope you can see a little bit of a pattern here. We keep adding again and again and again and again and again. Eventually we get a square with side length 1 and then width of 2, and its area, which is length times width, equals 2. And this is what I mean by summing all of the areas or summing all the terms in the geometric sequence. We should get 2. A bit of a example that really requires you to think about the mathematics, but also a different kind of example. Now, if we have a convergent series, that is a series that goes to 0, how I know this series is convergent is the common ratio is between 0 and 1. The formula sort of changes a little bit. Instead of having this formula here, the formula we actually have is s to the infinity, and it looks really nice here. S to the infinity equals a divided by 1 minus r. So if we wanted to sum to infinity the geometric series that had the first term 6 and a common ratio of -0.2, we can use this formula here, substitute in our known values, and we get the sum to infinity. It's really neat. we should get here the sum to infinity is actually 5. Now you can't actually double check that because it's impossible for you to add up an infinite amount of terms. However, you just need to be reassured that the sum to infinity is 5 for that particular geometric sequence. Okay, just one more quick example for you. The first term of a geometric series is 20 and the sum to infinity is 15. We're being asked to determine the common ratio. If I use my formula for the sum to infinity, S infinity equals A divided by 1 minus R, I get something that looks like this, substituting in my known values. My first term is 20 and my sum is 15. I'm being asked to work out my common ratio. First thing I need to do is multiply both sides by 1 minus R, and I get 15, open bracket 1 minus R equals 20. Next thing I'm going to do is divide both sides by 15, and I get left with 1 minus R equals 20 on 15. And then I can rearrange this for R, subtracting 1 from both sides and then multiplying by negative 1. I get 1 minus 20 on 15, and this equals R is negative 1/3. My common ratio is negative 1/3. This concludes everything that you need to know about geometric sequences.